Hello, welcome, and thank you for joining us today for this Hopkins at Home webcast, the James Webb Space Telescope, Revealing the Early Universe. My name is Emily Maharis. I'm a thermal engineer at the NASA Goddard Space Flight Center and a recent Hopkins alumni, where I received my bachelor's degree in mechanical engineering in 2020 and my master's degree in 2023. Since joining NASA in 2020, I've had the opportunity to work on a variety of spacecrafts and instruments, focusing on the thermal engineering design, analysis, integration, and test support. Some of the exciting projects that I've had the opportunity to work on include Dragonfly, IMAP, JPSS, and Illumity. It's a pleasure to host this discussion today, where over the next hour, we'll learn about how JWST has made enormous strides towards answering many of the questions we have about the early history of the observable universe by observing how stars and galaxies formed 13 billion years ago. I also hope that today we'll be able to answer your questions. So after this presentation, I'll be monitoring our virtual Q&A, and I encourage all of you watching live to please leave your questions in the chat below. We'll do our best to answer as many as we can. I'm joined today by Dan Coe and Taylor Hutchison. Taylor is a queer astrophysicist from Texas, studying some of the most distant galaxies ever found in our universe. As a NASA postdoctoral fellow, Taylor uses data from JWST to conduct her research on galaxies that existed less than 1 billion years after the Big Bang, which she studies by observing rest ultraviolet emissions that have been redshifted into their near-infrared spectrum. Also with us today is Dan Coe, and he is an astronomer at the Space Telescope Science Institute and an associate research scientist for JWST, discovering and studying some of the most distant galaxies known. For the past 10 years at the Space Telescope Science Institute, Dan has also supported other astronomers using Hubble and JWST. For his work, Dan was a recipient of the 2023 Johns Hopkins Alumni Association's Distinguished Alumnus Award, which honors alumni who have typified the Johns Hopkins tradition of excellence and brought credit to the university by their personal accomplishment, professional achievement, or humanitarian service. So Dan and Taylor, thank you so much for joining us today. I'll hand it over to you.
Great. Thank you very much, Emily, and everyone for joining. It's great to be here. So Taylor and I are going to take you on a cosmic voyage back to the dawn of time with Hubble and JWST. So for me, astronomy has always put things in perspective. We're an insignificant speck of dust adrift on a majestic swirl. But we're also extremely lucky to be alive and get to enjoy art and science and love. We came from literally nothing. And now, after 13.8 billion years of cosmic history, humans may be the pinnacle of creation. We're able to not only contemplate our origins, but also create giant telescopes and launch some of them into space to literally look back in time and see where we came from. So we ask questions like these: how did we get here? How did the stars and galaxies form? And this is what Taylor and I will talk about today. Then, of course, we also, astronomers also study how did planets and life form. Maybe that could be another episode. So this is one of the images that Hubble took about 20 years ago. This is the Hubble Ultra Deep Field. And I got to work on this when I was a grad student at Johns Hopkins. And so, and Hubble, by the way, it's 34 years old now and still going strong. It was launched in 1990. And so when I was a grad student, I got to measure the distances to these galaxies. And then across the street, Frank Summers produced this video. We're actually able to fly through all of these distant galaxies. And these galaxies are so far away that their light took billions of years to reach us. So we're actually looking back in time to seeing how these galaxies were. And what we find is that they're a lot smaller, and they had yet to form into these, giant, beautiful, spirals. They were a lot more irregular and clumpy. And then we get back to the earliest times. We see over here these pale red dots in the early universe. And they're red and even infrared because the universe has stretched the light to the infrared wavelengths and redshifted them. But we know that the galaxies probably looked more like this. So this is a tiny galaxy that's a lot closer to home, and we see a lot of detail in it. So we want to be able to see more details in these distant galaxies, but they're really small. So one of the tricks we have is called gravitational lensing. So this is other work I got to do when I was a grad student at Johns Hopkins. One of the main cameras on Hubble is the advanced camera for surveys, and that was led by Professor Holland Ford at Johns Hopkins. And so I got to be part of that team, and we used gravitational lensing to magnify these distant galaxies. So you see these beautiful arcs. These are distant galaxies that are stretched out, and so we're able to see a lot more detail than we would otherwise. And so gravitational lensing works like this. You have mass that bends space according to Einstein's relativity, and light follows these curvatures in space-time to us, and it can actually take multiple paths, and we can see multiple images of these distant lensed galaxies, and they're magnified, so we're able to see more detail than we would otherwise. So it's a really great tool that I've been using for the past 20 years or so, and not just myself, but other astronomers. So I did that when I was a grad student, and then I went on to lead my own Hubble program, and I took images like this. And so this was beautiful. We're seeing all of these amazing lensed galaxies here and all this detail. And then this happened. And the JWST just blew us away. I mean, it was just amazing, this level of detail we're able to see. And then you can, flip back and forth, as some of you might have done when this image came out. There were these comparisons, and you can just see all this detail that we were excited for JWST, but it's even exceeded our expectations, and we're just so excited to be getting to work with it. And here I'll pass it over to Taylor.
Yeah, so just to give you a little bit of background about this telescope, because Dan and I are incredibly obsessed with it, as with everyone who works with it is. This is an artist's rendition of what this telescope looks like. It's currently in space, about 1 million miles from the Earth. It is 6.5 meters of diameter, so it's a massive telescope. And it is meant to look at, this infrared light in these distant galaxies and exoplanet atmospheres and lots of really amazing science. The next week. So it launched December 25th, 2021. I don't know about Dan, but I was awake at 7 a.m. in Texas and watched this and absolutely cried when I saw this particular video, because what you're seeing in the video is literally the telescope moving away from us. It's the last view we get of this telescope on its journey 1 million miles away to its new home. And so it took 6 months to get there and then get ready, and lots of work done by many, many amazing people, which the next slide will show. We have including some of these leading people, like the big faces that kind of run the telescope. And so this is one of the most amazing images. This was in July of 2021 or 2022 when they showed off the first images from this telescope to the president and the vice president. And actually, the person in the far right corner is Dr. Jane Rigby, who's the senior project scientist of the telescope. And fun fact, she also just got this amazing award, the Presidential Medal of Freedom, for not only her work, but also for, kind of leading the charge with the JWST. But it's definitely more than just Dr. Rigby. It is actually a massive population of people who were involved with running this telescope. The next slide actually shows a really beautiful comparison of just a 2-scale model of this amazing telescope, and then just a fraction of some of the people that have been involved with working on the development, the, creating of the telescope, the testing that was involved, getting it onto the launch pad, launching into space, and then making sure it was working once it got to its new home. And so it's absolutely a feat of engineering, and thousands of people are involved in the making and continued running of this telescope. And it has amazing data, which we'll show you now. So if we go to the next slide. So the final place that we want to talk about was specifically with this telescope, from the running it side. Mission control for this telescope lives at the Space Telescope Science Institute in Baltimore, on Johns Hopkins University campus, which is amazing calling card for the university. This is a picture showing some of the mission control room, which you have to badge into. It's very fancy. They talk to the telescope frequently, and it's really the hallmark of the operations with the telescope. So as far as the things that we're going to show you, I'm really fascinated by the chemical composition of the universe. And so just to kind of help set the scene, at the very beginning, there was the Big Bang. And more than the Big Bang, there was hydrogen, helium, and some trace amounts of lithium. You might see we're slightly showing you lithium here on the periodic table. And that's really all there was. And then as the universe continues to grow and get more complex, and we have the first stars forming and the first galaxies, we get all of these other elements. And this is the entire periodic table. And what I really love about this particular depiction is it's showing you, in the top, you can see the different types of, astrophysical processes that are creating these different elements, and including also in the bottom corner, human-made ones. But in general, if you were to see the middle four, these are made from stars that are dying or that are interacting with each other, or neutron stars that are merging. So just like the lifetimes of stars creating so many of these elements that we are made up of and that we work around every day. And so it really, ties back to that amazing Carl Sagan quote of "we are made of star stuff." And it is actually very true. So if we were to look back at this gorgeous image that Dan showed earlier, one thing I love about galaxies and fields that have gravitational lensing is it kind of looks like you've asked AI to make a field of galaxies, because you have these weird light squiggles and stuff, but that's just the effect of gravitational lensing, which is really beautiful. But one thing in particular is, like Dan highlighted, the gravitational lensing kind of acts like a cosmic telescope, and it can help you peer into the very far reaches of the universe at light that would otherwise be impossible to see. And so one really cool effect of this is using spectroscopy to find these distant sources. And so in particular, this is one of the first spectra that were shown. Honestly, it was I think the next day after we showed the first images to the president and vice president in 2022. And I was, I think, driving my cat to the vet this day when they showed this, and I had to pull over and cry, because this is a light fingerprint, essentially, of a distant galaxy that existed over 13.1 billion years ago. And what you're seeing here is signatures of oxygen and hydrogen and neon, and so many different signatures that we, would spend years trying to get with these massive telescopes on the ground. But with this amazing space observatory, we can get all these at once. And what I think is really beautiful, if you go to the next, is the way I like to describe spectroscopy, like I've said before, is you can think of it as like a unique light fingerprint. And I would imagine if we're talking to alumni from Johns Hopkins, this is the perfect crowd to bring up the Pink Floyd album cover. When I showed the youth this, they don't know what I'm talking about. But essentially, the beautiful concept of you have this white light coming into a prism, and on the other side, you have this really beautiful rainbow. And so it's essentially splitting up the light into individual little light components. And so every single cosmic thing in space has a unique light fingerprint. So stars, galaxies, exoplanets, everything has a very unique signature that you can look at using spectroscopy. And so this is just an example of these very distant galaxies. So another really cool feature that JWST has, I mentioned it's a feat of engineering. It has a really funky kind of spectroscopy that is also on board. And this is called integral field spectroscopy. And all you really need to know about this really weird, awesome way of using a telescope is you get both the spectrum, this light fingerprint, and also images at the same time. And so the way you can think about it is, if a picture of a galaxy, every single pixel has a unique light fingerprint. It's a really fascinating feat of engineering. And to have it on a space telescope is amazing. And so if you want to see what this looks like, we have this animation that shows you, we're just walking through, certain kinds of light. So you're seeing hydrogen and nitrogen light for this lensed galaxy. That is the circle that pops up, you might see, around the center thing, which is the galaxy that's actually warping the light from the distant galaxy into that circle. As you can see, as we walk through these particular elements of this light that we're seeing, you can see the background galaxy pop up. And it's really cool. And so this is the kind of science you can do with this telescope. And so another cool way to look at this is, I just showed you that little animation, but truly, each pixel has this unique light fingerprint. And so this is a really interesting visualization where you can kind of zoom in on the pixels and you can see each of them have that little signature. And so you can look at the hydrogen and nitrogen light in every single pixel. And also a really cool thing, the next slide, is these pixels in particular for this galaxy are merged together. You can notice that all three of these little bumps are kind of blended. And this is actually a possible signature of a supermassive black hole in the center of this very distant galaxy. And so these are the kind of things you can start to pick apart when you have something like spectroscopy.
All right, thanks, Taylor. I'll take my turn here. So we're gonna now go into the even more distant universe and talk about some of these galaxies we've been looking at. And I wanted to mention that with this the lensing effect that Taylor also showed there, that it might seem a bit abstract, but you might find a similar example as close as your next glass of wine. The lensing effect is kind of like at the base of the wine glass. Like you see this as I move this around, you can see these lens images of these background objects. And so let's see if I can see where I am here. There we go. And so this is one of the effects that we've been using. And here you see these three lensed images of one of the most distant galaxies known. This was at the time when I discovered it 10 years ago. It was the most distant galaxy known with Hubble. And I waited 10 years, and then we finally got to look at it with this new telescope, JWST, and we were able to see multiple components in this galaxy. And we're actually, it feels like we were like splitting the atom. We saw this really tiny dot, and then now we're able to see these smaller components to it. So this is work led by my grad student Tiger Shao and postdoc Abduroff, both at Johns Hopkins. And so there are these really tiny pieces of this galaxy that we weren't able to see before. And just to put this in perspective, so here's this rendition of our Milky Way again. And if you put this to scale, this is such a small I mean, this is an entire galaxy that we're seeing in the early universe, and this is sort of typical of how big galaxies were back then. They were much smaller, and so over the next 13 billion years or so, this galaxy probably merged with hundreds or even thousands of other galaxies to build up to these massive galaxies like we have today, like our Milky Way. And then the spectroscopy, like Taylor was talking about, our friend Rebecca Larson was the first to identify these elements in this particular distant galaxy. And we see hydrogen, so one of the basic, the most basic element that was produced, from the Big Bang, but then also carbon and oxygen and neon. So we see that even just 460 million years after the Big Bang, a lot of these elements were already in place. So produced by these massive stars, which then, maybe went supernova and exploded and spread these elements, throughout these galaxies. So we've yet to go back far enough and see galaxies that are just made of pristine hydrogen and helium. And that's sort of one of the main goals of JWST. We're just in our second year, and it's exciting that all of the galaxies we've looked at, they've all been enriched in this way already at these early times. I want to show you one more galaxy at a similar distance that we discovered in my Hubble program relics. And so this my postdoc Brett Salmon discovered it and affectionately named it the Smudge. And my wife often tells me that I should maybe find more beautiful galaxies that these are they're not a lot to look at, but I mean she jokes and she's proud, but for this distance, in the first 500 million years, we were excited. We were able to see this much detail with Hubble. And then I sort of skipped ahead to the punchline here, but then we got to look with JWST, and we saw so much more detail again. So we can kind of flip back and forth here, and we see these amazingly tiny components. This galaxy is magnified by even more than that other one. The other one was a factor of 8 magnification. This one is stretched out to a factor of 60. And so we're seeing these really tiny clumps. These are star clusters, like 1 parsec in radius. And the whole thing is probably like 25 parsecs. So putting this back on our scale with the Milky Way, just for size, we're probably talking about, this little tiny clump here is the size of this whole galaxy if you deconstruct the lensing and put it back to how it should really look. So, and then within that, again, we've kind of split the atom. We're seeing these really tiny star clusters. And so we've now been able to do this throughout cosmic history, thanks to the beginning with Hubble and then also JWST with this lensing effect. We're seeing galaxy clusters like in our own galaxy. So Messier 80 is a galaxy cluster in our own galaxy. and it's probably 13 billion years old. And so we're now able to trace that back, 13 billion years ago, and to see how these star clusters might have looked in the early universe. So we haven't yet found the very first stars, but we found, some of the first star clusters. So this is like a giant leap towards finding the first stars. And again, very small sizes for these things, even smaller than the Messier 80. And this was some of the work we led with my cosmic spring team. So even smaller than that, to split the atom further, we've found individual stars. So this is just incredible. I mean, we didn't know that this would be possible before folks started doing this with Hubble. So these are in some very deep images that people took with Hubble. They were able to find these stars that were already billions of light years away in the early universe. And then with JWST, pretty much every time you take an image with JWST, it's like a Hubble deep field or better. So we now see these things all the time. Every time we look at a galaxy cluster and see this lensing, we see one of these stars that kind of photobombs us, and we're able to see individual stars in the distant universe. It's incredible. And this is probably the most famous one, the most distant. Earendel was discovered by my grad student, Brian Welch, who was at Johns Hopkins and then graduated, and he's now at NASA Goddard working with Jane Rigby and Taylor. And again, he discovered this with Hubble. This was incredibly exciting. And we knew that, this would, help fulfill the mission of JWST to study the first stars. And we were very excited to get to look at it with JWST. And, this is what we saw. I mean, you can go back and forth again. A lot of, details pop out. You don't see more details in Earendel itself. I mean, this is, a very small, to see individual stars like this in the early universe. We're not able to see multiple stars. But based on the colors, we actually see hints of a signature of different stars. So this is work that Brian led with JWST. And we weren't able to do this with Hubble at all because of the redshift. We were only getting to right about here with Hubble. Hubble gets you out to 1.7 microns. But with JWST, we could actually measure these colors. And what we found was what looks like we're seeing the sum of a sort of a hotter O star plus a still hot, but slightly less hot B star. So just remarkable that we're able to see, multiple stars the way we think. And we always thought Earendel would probably be multiple stars. When stars are this massive, they usually have companions. But we didn't think we'd actually be able to tell with JWST, but here we are. And so folks have done this with other stars, first with Hubble over here, and then with JWST for the other ones, measuring the temperatures and brightnesses of these distant stars and putting them on this HR diagram, where we really understand how stars form and evolve in the distant universe. But really, to understand stars better, we need spectroscopy, and I'll hand it back to Taylor to talk about this.
Yeah, so this was a really fun recent result that we've had from JWST from one of the teams I'm a part of. We looked at this galaxy that was incredibly gravitationally magnified called the Sunburst Arc. And it's really huge on the sky compared to the tiny fuzzy dots we were seeing from the beautiful data that Dan was showing. And this source is a redshift of about 2.3. So, it's over 10 billion years ago that this galaxy light emitted and then traveled all the way to us. And so what you're seeing here is on the top, we have this, kind of sideways image of the entire arc galaxy. Remember that this light just gets stretched and magnified in different ways. But the really cool thing that came out of this was when we got our JWST data, including that really funky spectroscopy I talked about earlier, is we saw this really weird knot, is what we called it. We're like, this is a weird clump. It's a weird knot. We don't know what it is. That's one of the best things about astronomy and science in general, I feel, is you find weird stuff and you're like, what is that? Let's figure it out. And so from this work, we ended up, it later got renamed to Godzilla, which is a very good name. But from the spectroscopy, which I'm showing you an example on the bottom, we saw hydrogen, nitrogen, helium, sulfur, oxygen, neon, tons of different kinds of elements that tell you about the chemistry inside of the thing that we're looking at. It tells you what kind of object it might be and how it was composed, and a lot more information that gives you kind of insight into the historical context in cosmic space of where this object resides. And so from all of this work, we found that this weird knot, this Godzilla clump, is actually very similar to the Eta Carinae star system that's really nearby, the one that's, it's about 7,500 light years away. And it's very famous for being the stellar system with these two stars that are interacting. The bottom left corner shows you kind of an artist's rendition of that, of Eta Carinae specifically. And so we're pretty sure that we found an Eta Carinae-like star spectrum at this very distant, redshift, very high, early cosmic history. And so that's what we think Godzilla is. And it's through all of this beautiful data from JWST that we were able to even figure this out in the first place. And so this is a really exciting result that's like fresh off the press. So y'all are some of the first people who get to see it. And then one of the final things that when we talk about stars specifically, that is kind of one of the main goals of this particular early universe science case for JWST, is trying to find galaxies that have some of the first stars that were ever formed. So you might remember we talked about, in the beginning, there was hydrogen and helium and some lithium. And there wasn't much more than that. There were just, these very basic, some of the first elements that were formed, abundance of hydrogen. And so the first stars that would form were the ones that helped generate these heavier elements. And so that means that the first stars that formed would have mostly hydrogen and some helium in them. And so what that means based on physics is you would have these very massive stars. And so what you're seeing here is an artist's rendition of, a few different famous stars, including our sun, and the relative sizes, and then a first generation star. This is what we call population 3, which is a weird astronomer backwards notation. But essentially, it's just like the first stars ever formed, so mostly hydrogen. And so they would be enormous and incredibly bright, and also possibly very short-lived relative to stars that we see closer to us. And so this is the big question of, can we find these first generation of stars? And with JWST, there's a very high chance that we can. And so there are active studies ongoing, including a program I just got awarded time for this next year. And we're going to try and find these galaxies that have some of the first stars ever. And so this is a really interesting, looking forward, I thought, of what we can do with JWST. And then speaking of looking forward, so another really cool recent result that happened is we're continually pushing the benchmark of the most distant galaxies we can find. I know Dan showed you some gorgeous spectra of these galaxies at redshift 10, which is enormous. It's double digits. And that is just something I did not envision was possible before this telescope launched. And now you're seeing on this slide, we have redshift 14.3. That is only 290 million years after the Big Bang. So that's over 13.5 billion years ago. So you're seeing essentially a baby image of one of the first galaxies. And so we're continually with JWST just pushing that benchmark further and further. How far back in time can you look? And so stay tuned. We're going to find more. As the lifetime of this telescope is, it did so well and it was so efficient with getting out to where it was supposed to be. Everything worked perfectly, which really, speaks to the amazing engineering and work that everyone involved with the telescope did. We have probably 20 years with this telescope. So we're going to find so many more cool things. And this is kind of just the beginning. And then finally, there's always more, right? So every time you have a telescope and you're hearing everyone launch, just a fun note, there's always at least 2 more in the pipeline that we're working on. We're getting ready to send them. And so in this case, the Euclid telescope, run by the European Space Agency, is actually already up in space and taking data. So we'll have really cool results from that very soon. And the Roman Space Telescope, which is actually currently being built, I get to see it on NASA campus often. I'm very fortunate. That's going to be launched soon as well. And we have more in the pipeline that we're working on too. And so there's this steady stream of continuing improvements in technology and telescopes. And both Euclid and Roman specifically will help us look at so much more of the sky and find even more weird things in distant galaxies and all this really cool science. And so definitely stay tuned. But that's kind of we just gave you a Cliff Notes version of some of the awesome work that's been done with JWST at these very distant early cosmic times. But yeah, thank y'all so much. Thank you so much, Taylor and Dan. We appreciate the look into how scientists like yourself are using Webb to learn about the origin of the universe. And all of the pictures you showed were beautiful. So now we'll go into our question and answer section. So we'll be opening that up online. And I encourage everyone in the live audience to use the chat feature below to post questions you'd like to ask Taylor and Dan. I'll give a few minutes for some questions to start rolling in. But as we wait for that to occur, I'd love to ask both of you, what potential future results are you most excited about with JWST?
Want to go first, Taylor?
Sure. Yeah, I everything we just talked about, I'm obsessed with. So we're just gonna like say that and set it aside because really the thing I'm actually most excited about is what weird thing are we gonna find with this telescope? Like every time we have an improvement in technology, especially if it's related to like an amazing new telescope, especially if it's in space because the atmosphere is frustrating for astronomers. We find new weird things that just tell us more about physics and more about the universe and ways that we weren't necessarily expecting. And so with, the Hubble Space Telescope, one of the things we discovered was we could find galaxies at increasingly far away from us by just looking at the colors at different wavelengths. And with JWST, I'm really curious to see like what weird or funky thing are we going to find that we weren't expecting that will kind of help better inform our understanding of how the universe evolved.
Yeah, it's great. I mean, it's so exciting and emotional, like Taylor said, to be able to get these images and learn all these things. And I think even more generally, just one of the things, just how excited the public has been, and just how. I mean, because Hubble took such great images, and the fact that the JWST has been able to also inspire people. I mean, it's that much better. It's this new telescope for this generation, and just how accessible it all is. I mean, I feel like the science has been accelerating. We get these images get taken, and then we're often able to see them like that same day and to analyze them. There's all of this software that's already written now, and so I think it's just generally becoming a lot more accessible. We're kind of lowering the barriers for for everyone to get involved. Other astronomers and also just people in the public who've been able to work on these.
Yeah, I think that's awesome. That's super exciting. I agree that the accessibility of all the images. I don't work on JWST firsthand, but I love following along. And I, too, am very excited for all of the weird things that you guys can discover with it. So moving on to the questions online, our first one is from Paul. He asked, it's wonderful to see photos of those who made discoveries. I've always wondered where the names of these stars and galaxies come from. Does whoever find it get to name it, or are there any other rules around that?
Yeah, I could tell the story of Earendel, for example. So yeah, when Brian Welch discovered it, I encouraged him to name it. I guess some astronomers have different opinions about this, but I thought it's great. Let's give it a cool name. And he suggested Earendel, and it's from like the Lord of the Rings and the Silmarillion. And I to be honest, I wasn't totally convinced at first. And then he explained the whole story of it, and it fits really well. And it's also an Old English word for the morning star. And I thought, oh, this is perfect. And then since then, I think Colbert ran with it on his show and was real excited about it. So yeah, I think we often get to name things. There's official names that go through the IAU, and they really have to vote on it. But for fun, we often just give things nicknames.
That's awesome. That was a good question. Next, Nathan would like to know what multiple lensed images of an object, or with multiply lensed images of an object, are the images at different times? Is this a way to simultaneously observe the same object at different points in cosmological evolutionary time?
I suppose I've worked a bit more on lensing. I could take that one too. But yeah, so there is some time delay, we call it, between these different images. And so yeah, just when you see these different light travel paths, I think I have it in the animation here. They'll take a different amount of time to reach us. I suppose the animation shows them arriving at the same time, but in practice, they could be days or weeks, months, even years apart. And so we've been able to use that, for example, to constrain cosmology. So like the Hubble constant and the whole expansion history of the universe, and which there's dark energy that we don't really understand. So there's this one here called supernova Hope. That was a type 1A supernova, so the same type that people use to measure the expansion of the universe. Now it's being lensed, And so they were able to use that as an independent measurement. And so, yeah, it's there's a lot of interesting science you can do with that too. I don't know if I fully answered the question, but I think.
Yeah, super interesting. I think this is a good question for Taylor, coming from David. What causes the redshift in light as it travels through space and time? Is it interactions with gas clouds or other matter in space?
That's a great question. So really, you can kind of think of it. I like to use Earth-friendly or Earth-centric examples when I talk about space because it is so vast. It's kind of hard to understand, even for me, sometimes conceptually. And also, it helps better process the thing I'm about to throw at you. So the space is so vast that it also just takes time for light to travel. Like even with the speed of light, things are so far away that the speed of light is not fast enough to instantaneously appear somewhere, right? Like, so if you're in your room and you turn on a switch, like immediately the light is filling the room. But if you were to look at the sun, which is about 8 light minutes away, if we had like an evil wizard come and like disappear the sun, it would take 8 minutes for the rest of that sun's light to reach us. And then for us to see that the sun is gone. And that's the sun that's near us, right? And so if you think about galaxies that are millions or billions of light years away, it just takes time for that light to reach us. And so, like I said before, we're kind of seeing, like in this picture, you're seeing a baby image of that galaxy. That light left that galaxy 13.5 plus billion years ago and traveled to us. And so as that light is traveling, it's going through space-time and the universe is expanding. And so you're having essentially the shifting of wavelengths of light. And so the light that was emitted from that galaxy in the ultraviolet, by the time it reaches us, we see it in the infrared. And so it's this really interesting concept. Like if you were to transport there, if this still exists, if you were to transport to this galaxy and look at the ultraviolet light, it would be in the ultraviolet. But because it's so far away from us and takes so long for light to travel to us through space-time, we see it in infrared. So everything has shifted and stretched is kind of the concept. And so that's effectively what redshift is. It's just describing, you could think of it as either describing cosmic time, how far back in cosmic time is it, or the distance as well of how far away these sources are, if that helps.
Yeah, definitely. I think I'll ask this one because it's a follow-up question or another question on redshifts. How do working scientists approach higher and higher redshifts? Are high values reliable or can they be prone to more error? And lastly, do they cause any concern/worry as you gather and analyze observations?
Go ahead, Taylor.
Yeah, such a good question. It is actively a field of study. So I mentioned before, like having double-digit redshift numbers. So really, really distant universe, like less than 1 billion years after the Big Bang. And present day is 13.8 billion years after the Big Bang. That is really, it was almost impossible to do before this telescope, just because the kind of light we needed was so faint and we needed to be outside of the Earth's atmosphere that we couldn't do this without JWST, mostly. And so what's interesting is, what Dan's showing right now is actually like work from that I was a part of, and then also part of my PhD dissertation, which it took like 6 years to do, and 2 bumps of light, carbon light. And that's as much as we could do when we were working with like a 30-foot wide telescope on the ground. And then JWST comes along and has those gorgeous spectra like this one, where you have tons of different elements seen at once. And this took maybe 2 hours instead of 6 years. And so it is absolutely like a continually growing field. As you try and find these more and more distant sources, you have to have, telescopes that are sensitive enough. And so the cool thing about JWST is we have both the spectroscopy that you see here. We also have the imaging, which you can kind of see in the band on the top. And so with the imaging, we can look at different kinds of light with the camera on JWST. And you can see, when do certain galaxies appear and when do they disappear? And depending on that information, you can get a fairly good constraint on how far away these galaxies are. And so that's kind of how we find these really distant galaxies. But kind of as another part of your question, it is still hard to do. And the further away a galaxy is, the less of these images you're going to see it in, because it's just so far away that the first light from it is going to be in some of the most infrared images only. And so that's when it becomes this interesting kind of conflict in our field of like, is this reliable? Do we trust it? And one of the best ways to prove that something is at the distance that we think it is to get a spectrum, because you see these bumps of light of these different elements, and that is the most precise way to know exactly how far away something is. So once you get spectroscopy, you're golden. But if you just have imaging, there is absolutely always a little bit of uncertainty on how far away something is.
Great. Thanks for that insight, Taylor. Next question that Michael wants to know is, since size and mass are not necessarily correlated, how does the mass of the large early stars compare to the most massive stars that form today?
Yeah, I suppose I could take that. Taylor mentioned that the very first stars are probably supermassive and much more massive than stars that we know of. And I think people have found up to 100 or maybe even 200 times the mass of our sun for some stars in our own galaxy. Whereas the very first stars might have been 1,000 or, well, we don't really know like how big they were. We haven't seen them yet. But for some of these stars that we have seen and studied, so far they're massive. I mean, the fact that we're able to see them at all is just remarkable. But they're probably, like around, like Earendel, for example, is probably 50 times the mass of the sun or more. We have seen other stars like that, so it's not too extreme. So it kind of fits within what we know about massive stars. But there's a lot more to learn about them. Yeah, I think so far we're just seeing the tip of the iceberg. I mean, we're seeing the massive ones. Someday, we hope to have an even bigger telescope and really be able to see, stars like our sun in these distant galaxies that we can't quite see yet for the most part individually.
Very cool. Sally asks, are there any new theories or surprising findings that you know of related to black holes?
Yes. Yeah, one of the biggest questions we have right now with the, extragalactic or outside of our own galaxy community is we're finding a remarkable number of very massive black holes in the centers of some galaxies at very high redshifts or very early cosmic time. And it is very odd because based on our understanding before this telescope of like how galaxies grow and evolve and how the black holes inside of them grow and evolve, because most massive galaxies in the universe have some kind of black hole in their center. And this is like an interesting conundrum that has been decades of study of like, how does a black hole grow first or does the galaxy grow first? Do they grow together? Are they interacting with each other at all? And so it's a really interesting question. And JWST has made it even more interesting because we're finding so many big black holes at higher redshifts than we were expecting. And so if you were to take the size, like, 1,000,000 times the mass of our sun, for example, if you were to take that size at, really early time, like, redshift 6, which is about 1 billion years after Big Bang, that means that it had to start at some point and it had to grow to 1,000,000 times the mass of our sun. And that is an interesting question because there's many theories on how a black hole grows and evolves. But our current understandings kind of really are pushing the theoretical limits that we currently have of how fast a black hole can grow to get the sizes that we're seeing at these very high redshifts. And so this is like a current ongoing field of study, is this really interesting question. And people are actively trying to figure this out.
Good answer. Moving on to Deborah, she asks, can you give a brief explanation on how the photos that you share differ from what our eyes would see if we were actually there, and why/how? She also has a comment on a side note that she wants to appreciate Taylor's earrings.
Oh, thank you.
Do you want to, or maybe I could do it because we have a lot of people at the Space Telescope Science Institute who kind of specialize in making these pretty color images, and they're people often ask about the colors, and they're about as real as we can get. So like Taylor was talking about, the light is stretched into the infrared, so we can't see that with our eyes. So it wouldn't do it's very good to make an infrared image. We couldn't see it, so they just compress that color range or wavelength range down into colors that we can see. And yeah, so we see these amazing pictures. And then I suppose, I often think about, especially with this lensing, if you were to travel towards it, the lensing would change. And sometimes I think about, in these distant galaxies, like the one I was talking about before, if I can find it here, that, these, we're seeing this galaxy as it was, 13.3 billion years ago. And you might imagine that, in that galaxy, there's, so many stars and planets, and maybe even life evolved and maybe made space telescopes that are looking back at us. And they would see something similar. They would see these pale infrared dots in their image that are also lensed, and they would see the Milky Way as it was over 13 billion years ago.
And then I think our last one in here right now is John had one additional question about redshifting. He said, I thought that redshift is a Doppler effect. Isn't that correct?
Yeah, it is. When I was describing the universe expansion, that's a feature. But it's helpful to explain for people who don't know Doppler effect. Earth-friendly example, if you're standing on a sidewalk and you have a fire truck zooming by you, you'll hear, first of all, the sound of fire truck approaching you, which is like, and then as it passes you, it goes, and that's literally sound waves being compressed in front of you and behind you. And so in the example I gave of where like the light's coming from this incredibly distant galaxy towards us, the universe is also expanding. And so you have essentially these sources moving away while also light traveling towards us. And so it's this combination, and Doppler effect is definitely part of it to describe redshift.
I don't know if you can see this. I grabbed another slide. Can you see this animation here?
No animation, no.
Oh, okay. It's on a different, well, I could try to move it around, but anyway, that was a good answer.
We'll see if any more questions come in, but one question that I wanted to ask was, I know that you talked about a lot of the things that you're excited for at JWST, but I was curious if you could share what has been the most rewarding part of working on JWST thus far. And you want to go first?
Wow, that's a great question. I mean, being able to look back and see these things. And by the way, this is the redshift we were asking about before. The space time is being stretched over the history of the universe, and the light is being stretched to longer wavelengths. That's the main component in this cosmological redshift. It's just been so exciting to, it's such an exciting time to be an astronomer working on these distant galaxies. I've worked on this lensing effect, and then kind of switched to using it to study these distant galaxies. And we're getting such amazing data, and seeing all the like Taylor said. Carl Sagan said we're all made of star stuff, and that stuff wasn't around in the beginning. It took all these stars making these elements, and the fact that we're able to see them now in these distant galaxies and really see where we've come from is just amazing.
Yeah, I think for me, the challenging aspect is that it's getting far more smooth now. But it's when you have a new telescope or a new instrumentation, you got to make sure it works properly, right? And you can test in a laboratory as much as you want how these things work. But the minute you get it into its new home, it's this vacuum environment in space a million miles from us, there's a very different experience that the telescope's doing, right? We do amazing testing on the ground, but there's only so much testing you can do to simulate the space environment. And so what was very interesting, like a fun challenge, but definitely challenging that first year or two, was you get this beautiful space data, but there's some noise in it, right? Like you have kind of like if you're recording audio, and so you record your podcast or whatever, and then you record silence. And that silence is not actually silence, it's like static noise. And it's you have to remove that static noise from the recording of your voice to get the crispest, clearest thing possible. And so in a very similar way, we have to process space data like this. And so the first 2 years are really interesting because we were having to clean this data as best we can and finding new, fun, weird things that were happening now that it's in a space home that we had to also adjust for. And so I actually find that really fun. It's like from a data science perspective, really fascinating to me. But it was a very fun and interesting challenge that we had to go through. It works perfectly, by the way. It's great. It works great now. But
yeah, well, thank you for both sharing your experiences and taking the time from your busy schedules to show these images and all of the work that you've done and research within the Hopkins community and on JWST. I'd like to also thank the live audience who tuned in today for our conversation. I appreciate all the questions that flowed through this conversation. I just wanted to let everyone know, if you enjoyed our program, please take a moment to fill out the event feedback form posted in the chat below. And additionally, if you'd like to share or rewatch today's program, it's going to be posted on the Hopkins at Home website and on JHU YouTube page in the coming days. So thank you again, everyone, and have a wonderful afternoon.
Yeah, thank you. Great talking to you.